That was after I got married.
Yeah, that's a problem.
Oops. All right, moving on. All right. Okay. Hey, real quick, we got a couple notes here to take. We're out of here at 12:55, so I want to do about 10 minutes and then give you about 15 minutes where you can kind of work. The section 2 that we're in, I think there's only 4 sections of Unit 4 that we're going into. I don't do them all in this unit. We just kind of hit the major parts. This is on optimization. This is the part that I've kind of been warning you of. Things that we get to where we figure out why we're using derivatives and why we're using this stuff. You guys have already figured out the big part of it, which are critical points and inflection points. But now it's actually like useful stuff for it. Now, there's a couple different things I want to talk about. Number one, graphs. There's graphs and table thing we have not seen yet. I want to talk about that today. And that's going to really kind of give us a taste for the stuff we haven't done yet. Okay, and then we have derivatives, or we'll do one derivative. I have 3 problems picked out today, and I want to go through them in less than 10 minutes. I don't know if we can do that. It might be one of those things where we just get as far as we can, and then I just kind of cut it off from there. Okay, so first of all, this is what a table is, and this is what I want you to be used to seeing here for this first unit. This is a very large table, and what you're actually looking at is they're giving you certain x values, x1, x2, x3 on a graph. You are not provided the graph. And then you're given what the first derivatives are doing at those moments. And you can if you want. This is just an intro. If you want to write it down. I'll give you some time. And then you're given what the x values are at those values for the y primes. And then you're also given the second derivatives. And what you're trying to do is figure out what does this graph, number one, look like. And do you have a max or a min? Like, where are those moments? So it's providing you the original function. So let me put this in there. They're giving you the functional information. That's these 3. They're giving you the first derivative stuff, which is the critical points. Okay, those are the critical points. And then why? All right, and second derivative. So second derivative, which is inflection. Oh my God! All right.
Look how critical that inflection.
What?
First critical.
Yeah, first derivative critical points, second derivative inflection. I'm just abbreviating. Sorry, I'm not writing it all on there.
I usually don't have enough cheeks to make it.
All right, just stop. Too much information. I don't want to have to edit this later. All right. So first of all, what we're trying to actually do on this problem is to come up with what does the graph actually look like a really rough idea. So the idea is that you have 3 x's, right? There's 3 values, and why they have them listed is because of like where the first derivatives are and second derivatives. That's why they have the 3 x's at the top. There's 3 like major things you're gonna have to look at. So on this graph, to the left of x1, wherever that's at, I don't know where x1 is, the slope is greater than 0. You can see that over here. I'm going to try to color code these. As we're going this direction up to x1 on the left side of it, we have positive slope. This is all positives, right? It's greater than 0. Then it's going to hit 0 slope. Then it stays positive as we go this direction. And then suddenly, as we get to this 0, it turns negative. So, if I'm kind of thinking about what can happen here, and this is a rough idea of this one. There's 3 x's. Whoa. Here's x1. I'm just guessing. Here's x2 or x3. Right? Whatever these are. Let's say these are my 2 parts. I'm guessing. As I'm going this direction up to x1, it's got to have positive slope.
Is x2 squared then?
What was that?
Is x2
When
squared?
you're done, will you go back to it?
Yeah, I'm going to go back here in a minute. This is a guess, right? So my slope is positive. It's going to level off to 0 at x1, and then it goes positive still for a while, right? Does that make sense? Mm-hmm. And then as I keep going, as I get past x2, it levels off again, and then it starts going down for negative slope.
2 x2s.
Sorry.
Wrong handwriting.
x3.
That's why I said
Yeah.
x2 squared.
Oh, yeah. Sorry. There was an x3.
Negative.
Whoops,
When you level off at x2.
No, on this graph, if you looked at it, it had positive slope through x2.
Oh, okay.
So so this is back to that first graph that if you want to see that, Erica. This thing was positive for a while. It hit 0. Then it still stayed positive, so it kind of like leveled off and kept going up. Then after x3, sorry, I had that missed typo there. Then it went back to 0. Now, that was a guess. That was a simple guess just by looking at the first derivatives. Now, what I would do next is I use the second derivatives to confirm concavity. Like, am I drawing this the right direction? Do I need to have it going a different way in general? So like on this one, the concavity here is down. It's less than 0. This is concave up. It stays down the rest of the time on this part. It was down basically for the rest of this moment. Okay? All right. Does that make sense?
Sure.
Okay, and so if I look at my graph, would I actually meet these stipulations? Would it meet, the certain moments where I'm going to have, a concave situation where it's concave down or up? Like, what is it looking like? So let's go back to my graph here, and let's see if I can clean this up. Up to that first X, it was concave down, like down. So the water's pouring out. Then it went concave up for a little bit. And then after, x2, it went concave down the rest of the time. So if I go back to my graph and kind of clean this graph up now, it was concave down up to this moment. Up to x1, it was concave down. Perfect. After x1, it was concave up until the point where at x2, it suddenly switches. This is the halfway point. And then it starts being concave down the rest of the time over here, which is exactly kind of the idea what I have going here. So if I was being more exact, I'd probably make this a smoother looking graph. It was going up, it kind of leveled off, it goes up, and it kind of makes this big horseshoe kind of a thing. So it was a big hilltop at that point. Okay, not so much as a level off like what I'm doing here. Okay, questions at all about, how do I use a table to graph?
No.
Now again, this day right here, I'm going to go back to this. This is just an intro today. I didn't want to do something super in depth. We'll do another 1 or 2 or 3 of these tomorrow, where it's just, can we get the graph and do we know how to put the information together by just looking at the data that's provided to me and getting a graph and a sense for where this thing is going without hitting specific numbers. Now, on these numbers, I didn't tell you what x1, x2, and x1, x2, and x3 are. On other, tables, they might say, x1 is 5, x2 is 10, x3 is 15, and they might tell you like these are the specific numbers I'm hitting. Okay. All right. Does that make sense?
Yup.
Okay. Does anyone need this chart still? Okay. Let me know when you're ready, and then we'll go on to the next. The next one is now. We talked about a table and a graph. My next problem is to talk about why do we use first derivatives? Why are we doing the stuff we're doing now? What is the way to optimize a problem? Right? So we're going to go back to that here in a second. And I'm going to give you the idea here. And this problem I picked here is out of your textbook. Okay. All right. So. All right. Okay, this is technically my last problem. I might need to move this thing over. All right. This is probably my last problem here today because I do want to give you about 15 minutes a day to work, so I got to be done here in about a minute. Okay. All right.
So I got 90.
The story problem based on this one, again, these are based on story problems in this optimization problem. We did some of this stuff back in pre-calc days where we tried to optimize, how much fencing would you use to make the biggest field possible. Yeah. Okay. I know it's been a while. We're learning the shortcuts in calc on that stuff. In pre-calc, how we did that stuff, we completed the square. What completing the square is figuring out where that vertex was for your parabola or whatever type of function you're doing. In calc, we learned the shortcut for it. The shortcut for finding the optimization, like the peak of a hilltop or the lowest point, is to just take the first derivative. So tomorrow I'm going to pull some of those problems we did in pre-calc. I'm going to pull those problems back up. We had some story problems. I think one was like an airplane. One was on a fence around a garden. Like I'm going to pull up that same slideshow we did back in Algebra 2 days, and we're going to use that and look at how we use derivatives to actually find those same answers. It's a way of optimizing. Now, what this story problem is for this, I know this is going to seem really weird. This is the radius of somebody coughing. like how it grows and where would the peak be for somebody coughing, and you know, like what was the range that this thing would hit, and I thought it was fitting. That's why that's the only reason I picked this problem out of the book. I was kind of reading. Yeah, it was COVID related. I was like, all right, that's a cool problem. I'm going with it. But anyways, it was in the book. If you want to read the story, it's in section 4.2. All right, now we're going to keep going here. So what they do here is they want to know what is the peak or valley on this particular problem. Well, this particular function, if we were to simplify it, that was the weirdest noise I've ever heard. If we're going to simplify this problem down and do the first derivative, we could either figure out if it's a peak or a valley on this particular problem. Now, if I'm going to kind of look at this, you know, what this function is, how you do this is you take the first derivative. So, first derivative, what do we get here? So, on this particular problem, I don't know why my palm is doing that. All right. Okay. So, I'm going to rearrange this problem just a little bit so it's a little bit easier to look at.
Are your knees weak or arms heavy?
What?
Is your Bombador sweater ready? Mom's spaghetti?
Oh my gosh, stop. I didn't realize you guys were quoting Eminem. Oh my God. I thought I had something on my shirt. So,
already.
well, I thought I had to pick up my son today. I thought he threw up on me. I didn't know. Oh my God, don't do that to me. All right. Okay. Okay. Oh, wait, hold on. What you're looking at here, sorry, I'm going to go back. This is the original function. This is just VR, just rearranged. Okay, so we do the first derivative here, and the first derivative is a product rule. So the product rule in this one, this is the first item, this is the second item when I do it. There is a multiplication between them. The first derivative of that r squared, I drop the 2 out front. So 2 times 0.1 is 0.2. R, I subtract 1 off the power. Then I take it times the second. And then I add the derivative of the second. Well, the second item, which is 9 minus r, the derivative of that is just negative 1, because the 9 would go away. The negative r would turn out to be negative 1, and the r would go away. And then you take it times the second, times the first, which is 0.1 r squared. So I'm going to stop there and let you guys get caught up, because I know some people are going to struggle at figuring out what did I just do there. It is derivative of the first, which is the 0.2r, times the second, which is the 9 minus r, plus the derivative of the second item, which is the negative 1, times the front, which is the 0.1 r squared. Is there any questions with how I find a certain derivative on that part? Like where the negative 1 came from, or the 0.2 came from, or anything like that? Okay, now, on this problem, to figure out, if we have a max-min, kind of what we're looking at here on this particular problem, there's a couple different ways to do it. I'm going to explain the easy way that I think of this problem, if it has a max or a min on this particular problem, just so you can see it. And then we'll kind of come back to it. They're giving me a limit here. I can't just go free range over this entire problem. I have a limit for all the r's that are between 0 and 9. So it's not a full continuous graph. There is a limit to this thing from there's a boundary set for it. The derivative here, if I simplify this thing out and actually kind of work with what am I actually looking at here? I have what is this? 0.18 r. I think that's 0.2 times 9. 0.2 times 9. 1.8. Sorry, I got the decimal in the wrong spot. 1.8 r. And then minus 0.2 r squared. So I'm just distributing this thing into this parenthesis. I'm just simplifying this thing out. And then this turns out to be negative 0.1 r squared. So if I combine like terms here, it looks like, and again, I'm just simplifying this thing down, 0.18 r, I have negative 0.3 r squares. That's if I combine like terms. So that's the first derivative. I'm going to leave it right there. So this is kind of a crucial part. We have to find that first derivative. Now, we're not finished yet. Okay, so what we're going to be doing here is figuring out where is the peak and valley, where's that critical point, if you will. That's like where a peak or valley is. And on this particular problem, I can tell if it's a max or a min. And this is something I hinted at yesterday, where what you do is you look at your function, the original function, and what I do is I plug in the boundaries. So what I would do on my original problem, I'd go up here and plug in 0, and I'd plug in 9 into this thing. And I would see what would happen. So if I were to plug in 9 into that thing, that whole function turns out to be 0. Right? Because it'd be 0 times 0.1 times 0, or times 9 squared, which turns out to be 0. So if I plugged in 9 down the road, it would hit 0 on the y-axis. If I plugged in 0 into this thing, it would be 0 again. So, and then any number that's between those two dots, 0 and 9, all those numbers would end up being positive. Now, here's how I know. If I were to plug in the number 1 here, what's 9 minus 1? It's 8. And what's 1 squared?
1.
That's all those numbers are positive. 0.1's positive, 8's positive, and 1's positive. So that number would be positive. It'd be up here somewhere. I don't even care where. It'd be positive. And any number, even if I go up to 8, let's say, and I plug in 8 in here, well, that would be 9 minus 8, still a positive number. 8 squared is a positive number. And so all three numbers are positive, so the answer would be positive even if I plugged in 8. So what I'm looking at here is all these numbers are positive, so probably what's happening is it's doing something like this, where there's a hilltop, because it's coming back down to 0 at some point. It's going to either be really steep. Now, there could be other things in there. So what I'm probably looking at on this particular problem is that this is probably going to be a maximum on this graph. Just because I can look at just the general, snapshot between 0 and 9, then I'm going to have numbers above 0, and so it's probably a maximum on this graph. And to find the maximum, that's when you figure out the critical points. I have to factor this thing apart. What do these things have in common? An R. Take out an R. So I'm left with 1.8 minus 0.3 R. And so my potential critical points here, if I factor this thing apart, this is the first derivative factoring. Right, I factor this thing apart to figure out the maximum or minimum. So if I factor this thing apart, it looks like this thing could represent 0. And this mess back here, if I set that thing equal to 0, it'll be 0.18 divided by 0.3. It ends up being a 6 back here. That would be a positive 6 if I set that thing equal to 0. And so there's two potential numbers there where I could have a maximum, and it's probably not 0. Why can't I plug in 0?
Because it's on the x-axis.
It's if you see where 0's at, that was not a maximum point. That was like almost the lowest point on my graph. So it was a relative min if I kept going right and left of it. So I'm not going to use 0. So this is probably my maximum number. So if I plug 6 in my actual graph, it'll actually give me what my maximum is if I were to actually plug this in. And this will actually end up being a max for this graph. The first derivative, just factoring the thing out, figuring out those critical points, actually tells you a max or min. Now, there's a couple different ways to do this. That's what we're going to look at tomorrow. So today was just kind of a really talk about the basics. And I know I might have confused you. Hopefully I didn't. We're going to look at some of these tomorrow, and I'm going to pull off story problems, and we're going to look at the ones we did in pre-calc days.
That's just finding
Max and mins. Yep. Yes.
You can grab that into
Yes, forgot.